A glowing slab of aircraft-grade aluminium is waiting between dies the size of rooms. Above it, the ram begins to fall, slow enough to watch, heavy enough to make the floor feel temporary. Workers stand nearby like scale marks on a blueprint. The press is so large that the building is not just shelter, it is part of the machine holding the force in place. Freeze the frame just before impact. Why did the United States need 50,000 tons of pressure to build the jet age? And why, decades later, are machines like this still almost impossible to casually replace? By the late 1940s, aircraft design had crossed a line that older factories were not built to handle. Propeller aircraft had already become complex machines, but jets changed the loads, speeds, and expectations all at once. Airframes now had to survive higher acceleration, harder landings, greater vibration, and longer service lives, while still staying light enough to carry fuel, weapons, radar, and crew. That combination created a brutal engineering problem. A jet did not simply need strong parts. It needed parts that could stay strong after thousands of pressurization cycles, repeated maneuvers, and constant fatigue stress. A tiny crack in the wrong place could grow with every flight. The traditional answer was to build large structures from many smaller pieces. Wings, bulkheads, landing gear supports, and engine mounts could be machined, drilled, riveted, bolted, and inspected into shape. That worked, but every joint carried a penalty. A joint meant overlapping metal. Overlapping metal meant extra weight. Fasteners added more weight, and every drilled hole created a place where stress could concentrate. Each connection also had to be checked, maintained, and trusted under loads that were getting more severe with every new aircraft generation. For early jet designers, this was not a small efficiency problem. It affected range, payload, reliability, and safety. The airframe itself was becoming a battlefield between strength and mass. The better answer was obvious in principle, but extremely difficult in practice. Replace complicated assemblies with larger single pieces. If a critical structure could be forged as one continuous component, it could be lighter, cleaner, and stronger, with fewer joints waiting to loosen, crack, or fail. To do that, industry needed a machine powerful enough to reshape enormous blocks of advanced metal in one controlled operation. A forging press does not work like a giant stamp that simply crushes metal thinner. The metal is heated until it becomes plastic, not liquid, and then the press forces it to flow. Under thousands of tons of pressure, the material moves sideways, upward, and around corners, filling the shape of the die cavity like extremely stiff clay. That flow is the key. Steel, titanium, and aluminium alloys are not just uniform blocks at the microscopic level. They have grain structures, and those grains behave a little like fibers in wood. The direction and continuity of those fibers can decide how a part handles stress. Picture an animation of a thick billet being machined into a curved aircraft fitting. The cutting tool removes everything outside the final shape, but it also slices through the internal grain. In the finished part, the grain lines run straight through the metal, ending abruptly at edges, holes, and tight curves. Now compare that with a forged version of the same part. As the hot metal flows into the die, the grain bends with it. The lines wrap around the curve, follow the lug, and continue through the areas that must carry load. Instead of cutting across the fiber, forging steers the fiber through the part. For an aircraft, that difference is not cosmetic. Continuous grain flow improves strength, fatigue resistance, and impact toughness. It helps a landing gear component survive repeated hard landings, or a wing fitting endures cycles of tension and compression without a crack starting as easily. Forging also changes the economics of large aircraft parts. If a component is machined from a huge plate or billet, much of that expensive alloy becomes chips on the factory floor. A near-net shape forging starts much closer to the final geometry, so less material has to be removed. The giant press was valuable because it could control both shape and internal structure at a scale earlier machines could not reach. It made the metal stronger by moving it into the right form, not by merely squeezing it flat. By the late 1940s, the United States did not just need better aircraft designs, it needed factories that could make the parts those designs required. Jet aircraft were becoming faster, heavier, and more demanding. Bombers, fighters, and transports needed large aluminium and titanium components with strength that could not be reliably achieved by older equipment. The bottleneck was not only in the drawing office, it was in the ability to forge and extrude critical structures at full size. That problem became a national manufacturing priority. Backed by the United States Air Force, the heavy press program was launched as a strategic industrial effort with a scale of roughly $279 million. Its purpose was to give American industry the machinery needed to produce huge, high-strength aircraft parts in quantity. This was Cold War planning expressed in steel, concrete, hydraulics, and factory floor capacity. The government did not simply order finished airplanes, it helped create the tools that could make the next generation of airplanes possible. The most famous results were two 50,000-ton forging presses. One went to Alcoa in Cleveland, Ohio. Built by Mester Machine, it began operating in 1955. The other went to Wyman Gordon in Grafton, Massachusetts. Built by Lowy Hydropress, it entered service later that same year. These machines were not laboratory curiosities. They were production assets designed to form major aircraft components that smaller presses could not handle. Wing spars, bulkheads, landing gear parts, and engine-related structures could be made larger, stronger, and with less waste. Military demand justified the investment, but the impact did not stay inside military aviation. As commercial jetliners grew in size and performance, the same heavy press capacity became valuable for civilian aerospace manufacturing. The heavy press program helped build the industrial base that carried American aviation from early jets into the wide-body era. The economics of a 50,000-ton press look strange until you stop asking how many different things it can make and start asking which things nothing else can make. A machine like this was not a general-purpose bargain. It was expensive, slow, and tied to a narrow class of parts. Its value came from changing the part itself. With enough force, a manufacturer could forge a larger piece of metal closer to its final shape, with the grain of the metal flowing through the part in a stronger, more useful pattern. That mattered because aircraft structures were often built from assemblies. A large component might require several smaller pieces joined by bolts, rivets, welds, or machined fittings. Every joint added weight. Every fastener added labour. Every interface had to be inspected, and every inspection step cost time. A heavy press could remove entire layers of that work. If one forging replaced a built-up assembly, the factory needed fewer parts, fewer workers touching the part, fewer holes drilled through it, and fewer chances for defects to hide at a joint. The press did not make manufacturing simple. It moved the complexity upstream into one massive forming operation. The savings could be dramatic. In one period example, a part that had started as a 1,600-pound aluminium slab, requiring about $18,000 in machining, could be made by heavy press methods from a 200-pound slab for under $2,000. Less metal was bought, less metal was cut away, and less machine time was wasted turning valuable alloy into chips. This is why the press could be both specialized and economically rational. It did not need to win on every part in the airplane. It only needed to win on the parts where older methods were brutally inefficient, or where smaller equipment could not produce the required strength and size. For ordinary components, a 50,000-ton press was overkill. For a wing spar, bulkhead, landing gear element, or engine structure that determined whether an aircraft could exist as designed, it was something else entirely. If a crucial aircraft depended on one of those parts, then the press was no longer just factory equipment. It became part of national industrial capability. The part begins as a billet, a block of alloy that may weigh as much as a truck. Before the press ever moves, that billet goes into a furnace where it is brought to a narrow forming temperature. Too cold and the metal resists the dyes. Too hot and the alloy can be damaged before it ever becomes an aircraft part. When the furnace door opens, the clock starts, Heat pours out in waves, and a massive manipulator reaches in with jaws built for glowing metal. The billet is pulled from the furnace, carried across the floor, and rotated into position while it is still hot enough to forge. At this scale, handling is part of the process. A delay of minutes can change how the metal flows. Under the press, the dies are waiting. These are not simple flat plates. They contain the rough negative shape of the component with cavities, ribs, bosses and channels designed to push the grain of the metal into useful paths. The manipulator sets the billet between them, then backs away. The press cycle begins slowly. Hydraulic cylinders drive the upper die downward with tens of thousands of tons of force. The billet does not shatter or splash, it yields. Metal squeezes outward, fills the die cavities, and begins to resemble a wing spar, a bulkhead, or a landing gear element. Excess material escapes around the edges as flash, proving the die has fully filled. Often, one squeeze is not enough. The part may return to the furnace, come back to the press, and be struck again in another die. Each heat and each pressing moves the shape closer to the final forging while keeping the metal workable. After forming, the glowing part is trimmed. Flash is cut away, edges are cleaned, and the forging goes through heat treatment to lock in the required properties. Then machining begins. Rough cuts remove large allowances. Finished machining brings holes, faces, pockets, and mounting surfaces to exact dimensions. The last stage is inspection. Technicians check dimensions, search for cracks, and verify the internal structure. Only then does the forged shape become more than a hot piece of metal. It becomes a certified aircraft component made by heat, timing, and force on a scale few factories could command. The first aircraft programs that justified these presses were military, but the need did not end when the earliest Cold War jets left the drawing board. Every new generation of aircraft carried heavier loads, flew longer routes, and demanded metal parts that could survive years of repeated stress without hidden weakness. Civil aviation inherited the same problem at larger scale. A commercial airliner needed strong wing structures, engine mounts, landing gear supports, pressure bulkheads, and fittings that could carry enormous forces without adding unnecessary weight. Forgings made under giant presses gave engineers a way to combine strength, reliability, and efficient shape in a single critical component. That is why machines built for national defence kept finding work in peacetime industry. The Wyman Gordon 50,000-ton press became part of this hidden manufacturing base, producing large aerospace forgings long after its original Cold War urgency had passed. Its capacity connected it to major American aircraft programs, including the era of the Boeing 747, when jumbo jets pushed commercial aviation into a new scale. The 747 was not just a larger airplane. Its landing gear, wing attachments, and structural members had to manage loads that would have been extraordinary only a generation earlier. Behind those parts were factories capable of moving hot metal with precision and forcing it into shapes smaller machines could not make. By then, the great presses were no longer dramatic wartime symbols. They had become industrial infrastructure, working in the background beneath American aerospace dominance. The aircraft changed from fighters to jumbo jets, but the requirement stayed constant: large, high-integrity metal parts made with force few machines on Earth could deliver. This is why retiring a 50,000-ton press is not like replacing an old machine tool. The press itself is only the visible part of a much larger system. The pit below it, the foundations around it, the hydraulic power, the handling equipment, the dies, the furnaces, the inspection process, and the workers who know how hot metal behaves when it is being forced into shape. A modern replacement would require more than money. It would require a site that can physically support the machine, years of engineering work, specialized contractors, new tooling, qualified operators, and customers willing to wait while the whole process is proven. Even after the press is installed, aerospace parts cannot simply move onto it overnight. Every critical forging has to meet strict quality standards, and aircraft manufacturers must trust that the new process produces the same strength and reliability as the old one. That makes the old press both valuable and difficult to escape. If a small machine wears out, production can often shift somewhere else. If one of the few giant forging presses goes down, the problem can reach into aircraft supply chains, defense programs, spare parts, and future production schedules. This is the late twist in the story. America built these machines during an era when it could mobilize steel, capital, government urgency, and industrial confidence on a massive scale. Keeping them alive has been easier than rebuilding that world from scratch. So the 50,000-ton press is not just a survivor from the 1950s, it is hidden national infrastructure, still carrying a piece of the jet age on its columns. Its age is impressive, but its importance is the real warning. As the ram finishes its descent, the glowing billet stops being raw metal and becomes part of an aircraft skeleton. The jet will get the photographs, the test flights, and the museum floor. The press stays behind in the factory, shaping the parts that let those aircraft survive speed, weight, and stress. That is the hidden bargain of the jet age. The airplane became famous, but the press made it possible. Thanks for watching. If you know another hidden industrial machine worth covering, write it in the comments.